So this talk is about Linux memory optimization and analyzing. I created this talk for system administrators. What I do in my normal life, I try to make Linux understandable for people that administer real-life systems. I'm not taking a developer approach in this talk. I'm just interested in how memory works and what people can do with memory in real life when working with Linux servers. So there's way too many things to talk about if you want to dive deeply into memory. So I picked out two common scenarios that are often encountered on Linux servers. Let's start with the first one. The first one is about understanding what really is happening with regard to memory on your server. So I took a display of free-m. You probably are all aware of this utility. Free-m gives an overview of current memory usage. And in this memory usage, you can see the total amount of memory that is available, which is 998 in this print. 768 megabytes used and 220 megabytes that is free. Now, the interesting thing in free-m is the second line, which is the minus plus buffer cache. In the minus plus buffer cache, you can see what is considered to be available memory if you think of buffers and cache as memory that can be claimed immediately in case it is needed for something. So if you look at this minus plus buffers cache line here, you can see there's 333 megabytes of memory in use and 54 megabytes of memory that is available. So from this point of view, you might think that you can load an application that needs 650 megabytes of RAM, which simply isn't true. So I dived a little bit deeper into this and did a couple of experiments. And yeah, what I'm presenting here is a more sophisticated approach on how to see what memory is available on your server. Now, if you want to do a simple test on your Linux system and find out what really is happening with the minus plus buffer cache line, if it would be true that buffers and cache is memory that can be used immediately for something else, then a command like echo3 towards the drop caches file, which drops all the memory that can be freed immediately. Now, this command should give you something like many used and 0 buffers and 0 cache at the moment that your memory is dropped. Now, if ever you are going to try to do this, you will notice that there is still some memory remaining in cache and there is some memory remaining in buffers, and that is simply because this memory is actively needed by the Linux kernel. So you can't just drop it because it's immediately claimed back. So that doesn't really make sense. So basically, free-m is lying. So about Linux memory, if you really want to understand what Linux memory is doing, you should have a look at the proc.mem.info file. Now, in the proc.mem.info file, there's a couple of interesting lines. There's many interesting lines, but in this talk, I'm just going to focus on 7 of these lines. Now, first, there's a difference between active and inactive memory. Now, the idea of active memory is that active memory is memory that is actively being used by the Linux kernel, and you really need it to be available in RAM. Now, inactive memory is memory that has been allocated and that still sits in RAM, but you don't really need it, and you can do something else with it. Now, there's a more sophisticated view to inactive memory and active memory, and that's the difference between the anonymous memory, which is shown as active anon, and the file memory, which is shown as active and inactive file memory. Now, the anonymous memory, that is basically memory that is claimed by applications, and the file memory, that is basically, roughly speaking, memory that is claimed by buffers and cache. Now, in order to understand this memory model, there's something else that you should also understand, and that is a virtual memory. Now, especially when talking to people that come from a Windows background, virtual memory is something very interesting, because Windows people think that virtual memory is the same as swap memory, which isn't the case. That is why I took the vmalloc total, so that is the total amount of virtual memory that is available on an average 64-bit Linux system. As you can see, that's a huge number. I think that's 3.5 terabytes. I don't have 3.5 terabytes in my laptop. You probably don't have 3.5 terabytes in your server. But it's the memory that can be pointed to from the perspective of the Linux kernel. Now, the interesting thing, what is virtual memory? It's an address space that programs can reserve memory in. The thing is that if you load a program, the program needs pointers to memory. And in order to create these pointers in memory, it doesn't really matter if the memory really exists as RAM or anything else or not. And that is why it's called virtual memory. So virtual memory in the sense that it doesn't really exist, and not in the sense that it is swap space. Now, at the moment that the process really needs the memory, it becomes resident memory. You will see a memory allocation happening at that moment, and normally for most programs you will see a huge difference between virtual memory and resident memory that's allocated. Now, in order to understand virtual memory, you should also understand overcommit. Now, what is the idea of overcommit? Well, basically, if you have like 3.5 terabytes of RAM and 3.5 terabytes of virtual memory, of course, and 4 gigabytes of RAM, the 3.5 terabytes of virtual memory is what really is usable by the Linux kernel. So programs can use addresses anywhere in this address space. And if you do overcommit, that means just simply that you are going to use a 3.5 terabyte address space in total, which is basically good because a process just needs memory pointers. It's not going to use the memory directly anyway, so it doesn't really harm to do overcommitting of memory. On the contrary, in many cases, overcommitting of memory is good because it increases the amount of programs that you can load. But also in some cases, it can bring lots of troubles. That's specific work scenarios. But before going in there, let's look at the following slide. Now, this slide comes from top, and what is interesting here is the vert column and the resident column. What you can see on this system, it is a small system that is just 1 gigabyte of RAM available and 2 gigabytes of swap. Now what you can see is that in the virtual memory column, if you take the total of all these amounts of virtual memory, I didn't take it, but it's at least 4 or 5 gigabytes. Now that is the idea. If you look at this for the first time and you really don't get the idea of virtual memory, you sense that something strange is happening here, because this system is using like 5 gigabytes of memory that doesn't really exist. Well, that is the basic difference between virtual memory and resident memory. In this column you can see the resident memory that's actually being allocated by processors running on this system. And that is also what is reflected in the memory usage lines that you can see in the upper part of the top output. So basically virtual memory is good. And this system, over allocation is good. Because if you wouldn't do any overcommitting of memory, well, there wouldn't be enough memory available to load all the programs that are currently loaded on this system. Now, how should you handle overcommit in case you don't consider it very good? So basically the idea is that overcommitting is allowed up to 3.5 terabyte of memory, but you can put a limit on that if you want to. In order to do that, there is the VM overcommit underscore memory parameter. That's a sysctl parameter. You can find it in the procsys file system. I hope you're more or less familiar with kernel tunables in the procsys file system. I'm talking about those here. Now, the VM overcommit memory, it can have 3 different values, a 0, a 1, and a 2. A 0, which means do overcommit memory, 1, which means don't overcommit memory, 2, which means do overcommit memory, but up to a certain limit. Now, if you want to do overcommitting of memory up to a certain limit, there's the overcommit ratio, which is an interesting parameter. You can give it a percentage that relates to the total amount of memory that's available in RAM and in swap. So if, for example, on this system I have 1 gigabyte of RAM and 2 gigabytes of swap, then an overcommit ratio of 200 would give me 6 gigabytes of swap. Could I please handle questions at the end of the session? I'm afraid I'm running out of time otherwise. So let's talk a little bit about memory usage as well. Now, this image that you see here has a memory total of, let's say, 1 gigabyte and a memory free of 460 megabytes. Buffers plus cache, which is about 170 megabytes. And that is just one way of looking at it. The other way of looking at it, it's the active and the inactive memory that is shown here. Now, the interesting thing about active anonymous memory is basically memory that is used by processes. You really want it to be available in RAM. Inactive anonymous memory, that is memory that is allocated as resident memory by processes, which currently sits in RAM, but you don't really need it there. The interesting thing of inactive memory is that it is a good candidate to be swapped out. Now, we also have active file and inactive file memory. Now, that relates to the memory that you have in your buffers and cache. As you probably are aware, cache is very good for a Linux system, because in cache, in the file system cache, pages are stored that are frequently accessed. And the fact of having these pages in cache makes your system faster. If you don't have enough cache, the system needs to get it from disk at all times, and your system will slow down. So having a lot of cache in general, especially for servers, is a very good thing. Now, what we can see here is that we have like 30 megabytes in cache that is actively being used, and 82 megabyte in cache that is not actively being used. Which means that if we have a shortage of memory on this server, there is a very easy way of getting more memory, and that is just to dump the 82 megabyte that is sitting in cache and that is currently not actively being used. That is also something that's happening automatically and that you can trigger by using the drop caches parameter from the proxys file system. So that's an easy way of making more memory available. Now, yeah, this is basically what I just all explained. So anon memory roughly corresponds to memory that's used by programs, and file memory is memory in cache and buffers, and the difference between active and inactive is very interesting. And what is interesting from the perspective of a system administrator is that active anonymous memory, you need it. Inactive anonymous memory, you can swap it out. And active file memory, you need it, and inactive file memory, you can just drop it. Now, that takes me to almost the last slide of this presentation. This is just numbers I made up, but it looks very similar to what I found at a customer site. The customer had real performance problems on the server, and the server was continuously relying very heavily on disk I/O. Now, what was happening here? As you can see, we have a memory total of 8 gigabytes, a swap total of 2 gigabytes, a memory free of almost nothing, and you can see a swap free of nothing at all. Now, the interesting thing here is that 2 gigabytes is available in active anonymous memory, and 6 gigabytes is available in inactive anonymous memory. And active file memory, well, almost everything in cache was being used actively. Now, what was happening here is that this system was under a lot of stress, but it's also a system that could be optimized very easily by working with the inactive anonymous memory, which is 6 gigabytes and which could be placed in swap. But this particular system didn't have enough swap, so the solution for this system was just to create more swap. So that is exactly what I did here. I increased the swap to 8 gigabytes, and I temporarily increased the VM swappiness parameter to relieve memory stress. And what you could see there is that swap was filled up pretty fast, and like 15 minutes later, all memory stress was released on this server. And that brings me to the end of my 15 minutes. Thank you very much for listening. Are there any questions?